Yeah, I'm good.
Okay, so it's a great pleasure to have Junxiao Wang from Northwestern University today here in the M seminar. So please take us away.
Yeah, okay. Thank you for the invitation. I'm glad to be here to give this small talk. So the topic of the title of my talk would be the Gamma Conjecture for tropical one cycles in local Miller symmetry. So the left page will be about the contents of the talk, and on the right blank page, I will just write some technical results or some computation when it's necessary. Okay, so basically my talk will consist of 3 parts. So I will first give a brief introduction to the Gamma Conjecture. So roughly speaking, it will consist about the central charges of dual objects in homological mirror symmetry. So mathematically, it will relate the period of some Lagrangian, some method to the central charge of its mirror object E. So in this talk, I will test this Gamma Conjecture for the Gross-Hilbert model for local mirror symmetry. So in part 2, I will give introduction to the Gross-Hilbert model for local mirror symmetry. In particular, I will consider about the canonical bundle for some symplectic, for some toric smooth surface. And the third part will be the main part of this talk. So in part 3, I will test the Gamma Conjecture for the Gross-Hilbert model. So in particular, I will consider about the coherent sheaf of the direct image of some structure sheaf of smooth curve inside the toric surface. And I will construct its mirror through tropical geometry. And I will show that the period of this beta t would be equal to the central charge of this coherent sheaf. Okay, so let me start from part 1. So part 1 will be the introduction to the Gamma Conjecture. So suppose YT is a mirror to some symplectic manifold with a family of symplectic structure. Then we can consider about the periods. Periods of YT will satisfy some Picard-Foucher's equation. So it will have a formal solution, which could be written as T equals to sigma K N, sorry, A N T to the N. Okay, so Hosono proposed that from this formal solution, we can construct a cohomology valued hypergeometric series, which could be written in this way. N plus nk in n plus j over 2 pi I. N plus j over 2 pi I. So here J would be a basis of the Picard group of X. Okay, we can rewrite this cohomology valued hypergeometric series as with respect to the basis of the K group of X. In this way, sigma J, JT, the trend character of Fj, where Fj is a basis of the K group of X. And in order to get the coefficient of this trend character of Fj, we need to take another basis. Another basis of the K group of X, such that it's dual to the Fi in the sense that sk tau x. The integral of this form will be equal to delta lk. Then we can get the coefficient of the Junxiao of fj by integral of this hypergeometric series with respect to tau x. Okay, so the Hosonos conjecture, the Hosonos version of the Gamma conjecture is that this coefficient fjt would be equal to the mirror, to the period of the mirror of Sj with respect to some holomorphic cone. So if you look at the leading term of this integral, which is basically a term where n is equal to 0, then the right-hand side will just be this integral. So where this is a gamma class of x, which is equal to the product of gamma 1 plus delta I, with delta I the chain roots of Tx. And you can also rewrite this term, this gamma class by the exponential of gamma C1x plus theta k k Tx. So this is the Euler constant, and this is a theta function. Okay, so in this talk, I will test this conjecture for the gross zero-Boot model, where the mirror, where we can get a mirror for the canonical bundle of some toric surface. So and I will take this Sj to be some special, to be some particular coherent sheaf, which is given by the direct image of some structure sheaf of the smooth curve. So C would be some smooth curve of in X sigma bar. And I will construct its mirror beta T through tropical geometry. So we'll construct beta T, which is a homology cycle inside YT, such that this beta omega T would be equal to the central charge of the Sj. Okay, so this is called the central charge of Sj. Okay, so in order to do this, I need to tell you about what's the gross zero-Boot.
Ask a question.
Okay. Yes.
The original conjecture is, what is the setting? Is X some any Calabi-Yau, or is there what is the kind of setting?
Calabi-Yau, I think.
Okay.
Yeah, I think so.
Okay. Thank you.
Yeah, I think so. Yeah, so in order to test this, I need to tell you about the gross zero-Boot model for this mirror construction. Okay, so in this talk, I will particularly consider about the smooth toric surface, X sigma bar, where sigma bar is given by some smooth complete fan inside R2, whose one cones are generated by these primitive vectors. And their corresponding toric divisors would be represented by D1 bar to dP bar. So the right hand side would be an example of this model. I will take the example to be P1 times P1. So this would be the fan for P1 times P1, and D1 bar, D2 bar would be a basis of the Picard group of P1 times P1. So the canonical bundle of the toric smooth surface will also be a toric variety, whose fan is generated by sigma bar times 1. So it's a fan over the sigma bar. And it also, it will have the one cons with given by this primitive vectors. So Vi is a vector over the Vi bar. And their corresponding toric divisors will be represented by D0 to Dp. And I will assume that D1 to Dk is the basis of the Picard group of the canonical bundle. And this is the fan for the Kp1 times P1. Okay, so in order to construct the mirror of the canonical bundle,
can I ask, is K P minus 2? Is K equal P minus 2?
It should be P1 times P1. So it should be
No, the question is, what's the relation between, you have two indices, P and K. So the question is K is always P minus 2?
Oh, yeah, right.
Okay, all right.
Yes. Yeah, right. Okay. Yes. Okay, so the idea of Gross-Hilbert model is that we can start from some real affine manifold with some combinatorial information, and with this information, we can construct the two families of complex schemes, and it's expected that these two families will be mirrored to each other. So in this case, I will start from this canonical bundle and get the information of this combinatorial information, and use this combinatorial information to construct the mirror of the canonical bundle. So in this case, the real affine manifold would be given by the convex hull, would be given by the union of the convex hull of the triangle times 1, 0, 0, 0, 0, 1. And another convex hull is the triangle times 1, 0, 0, 0, 1, minus 1. So here the triangle is a polytope inside R2, which is determined by these primitive vectors as its vertices. And I will take a polyhedral decomposition of this triangle by connecting the origin with its vertices. So in P1 times P1 case, it would look like that. And then this B would, in the P1 times P1 case, would just look like two pyramids with their buttons identified. And the polyhedral decomposition of B would just be induced by this P bar. So in this P1 times P1 case, it just be this tetrahedron. Okay, and the delta is the discriminant logs of that B, which is defined to be the first barocentric decomposition of P bar, which doesn't contain the vertices. So in the V1 time, in the P1 times P1 case, it would just be this red region.
I'm sorry, can I, so is B supposed to be three-dimensional, right?
Yeah, B is three-dimensional.
Why is it four-dimensional? I mean,
it's a three-dimensional subspace inside R4. So the reason that we embed it into R4 is because we can use this to give the affine structure of B.
Okay.
So yeah,
so it consists of, you know, those two three-dimensional pyramids inside R4.
Yes, right.
Okay, good. All right, thanks.
Okay, yeah, and I will call the codimension 1 cell row inside the inside the triangle to be the slabs. So in this case, this will just be the slabs. And every slab will be between two maximal cells of P, which I will denote by sigma rho plus and sigma rho minus. And the slab minus the discriminant logs will be the U9 of some components which corresponding to the vertices of the slab, and I will denote them by rho v. Okay, so we also have to give a affine structure for B minus discrete loops. And in this case, it will just be given by U sigma, phi sigma, UV, phi V, where U sigma is a interior of the maximal cell of P, and UV is a star neighborhood of some vertex of P. And the affine chart for U sigma is given by embedded into the affine space which contains the maximal cell. So in coordinate, it could be written by M maps M R1 R2 to M R2. So M is something inside M R2 or M R, which is just R2. And the affine chart for and the phi V is given by projecting UV along the direction which is determined by the vertex. And in coordinates, it could be written in this way. So this affine structure will induce a local system of integer tangent vectors, the affine manifold B minus delta. And I will denote, I will identify the fibers of the points inside U sigma by lambda sigma, and identify the fibers inside the affine chart UV by lambda V. So then this local system would have a monogamy, which you can regard it as a endomorphism from lambda V to V for the loop starts from UV to U sigma minus and to UV prime and to U sigma plus and back to UV. And in coordinates, the monogamy is given by in this way. So you can see that M0 is monogamy invariant, and it's corresponding to the tangent vector which tangent to the triangle, which is just the combination of the unite of the slabs. And I will call the integral tangent vectors tangent to the triangle by lambda rho. And I will also identify the fibers for the points over the triangle through parallel transport and denote them by lambda sigma plus. And for the fiber of the points below the triangle by lambda sigma minus. Okay, so given this information, we can come to construct what this YT should be. So we will start from some central fiber. So Y0 will be some central fiber, which could be given by the co-limit of P sigma. So P sigma is some toric variety determined by the point of sigma. By sigma inside the polyhedral decomposition. And they are glued in the way that whenever you have a subcell inside sigma price, you will glue this two toric variety along their toric divisor, which is just a P tau. So this will give you the central fiber of the family of YT. So the YT would just be the smoothen. Would be the problem about how to smoothen the central fiber Y0. So in order to do this, let's see the local model of Y0 near the affine chart UV. So locally, Y0 will just be given by the spectrum of C lambda rho, Euro plus, Euro minus, okay. quotient by UV plus, UV minus. So in this P1 times P1 case, if you look at that near the affine chart UV1, the affine chart will just look like that. And these two directions just corresponding to UV plus and UV minus. And according to this colimit, according to this green, they should satisfy that UV plus, UV minus would be equal to 0. So here UV plus is equal to Z 0, 1, V 0, 0 minus. And so with respect to the affine chart UV finally. Okay, so in order to smoothen it, we can actually, what we can actually do is we can replace this relation by some other relation. So locally we can consider this formal scheme. Should just be given by T1, Tk, lambda rho, UV plus, UV minus. Okay, so this would, so in order, so the idea of the smoothing process is just by changing this ideal to some ideal looks like that. So we need to determine the information of this kappa V. So this would just, sorry. So this kappa V will be determined by the information which is called multivalued piecewise linear function. So this could be regarded as the piecewise linear function on each affine chart. So phi sigma and phi V. And in this case, phi sigma and phi V would be determined by assigning every vertex of P to some parameter space of the Picard group of the canonical bundle. And in this case, we will map V plus to some non-zero element and V minus to 0, and VI to 0, 0, 0, minus 1, 0, 0, 0, with minus 1 on the ith position for I from 1 to K. And map phi tilde of VI would be 0 if I is not inside 1 to K. And then the kappa V, and then the kappa V, which is called kink, will just be given by the difference of slopes of phi V along the third coordinate. So in this case, it will just be given by Q minus phi tilde V. Yeah, so intuitively speaking, it would just be the used to measure the difference of the slope along these two directions, and that would give you the information for the kappa, for the KV is. Okay, so in order to get the information of what FV is, the idea is like that. So essentially, we are using this local model to group different affine charts. So lambda sigma plus T1 to Tk lambda sigma minus. The idea is that we want to use this local model to group these two affine charts, but we want to group them in a consistent way, which means that if we parallel transport UV plus UV minus to another affine chart. So in this case, the parallel transport will transport UV plus to Z to the V. Sorry, VV minus V prime, UV prime plus. And the parallel transport of UV minus will be U prime minus. So we want that ZV minus V prime V UV prime plus times UV prime minus satisfy the same relationship with UV plus times UV minus. So this will require that the function fv should satisfy this this condition to make this growing process consistently. Okay, and there are some other conditions for the fv. So we should require the constant term of fv to be 1, and we should require this normalization condition, which means that the log of v should have no terms of t to the q. So this normalization condition is kind of important because it will have something to do with log Gromov-Witten theory. But I will not talk too much about this here. So in the P1 times P1 case, the slab function fv0 would just be given by 1 plus e1 minus, would just be given by this formula. And you can see that the first terms of it would just be the same as in the definition of classical local mirror symmetry. And you would have some additional terms of t, which is just to make the slab function to be normalized. Okay, so combining this information together, we can finally give the definition of what yt should be. Oh, sorry. So the yt would just be given by the colimits of this spectrum. Okay, yeah, sorry. So I will call this I will call this ring to be RV. So the yt will just be given by growing the different affine charts through this spectrum RV. And strictly speaking, it should be a formal scheme rather than an actual family of analytic complex spaces. But in this talk, I will assume that you can always do a analytic extension of yt, such that you will get an actual family of complex analytic spaces, which is mirror to the canonical bundle that we care about. Okay, so after finish this, I can come to the third part of my talk, which is just testing the Gamma Conjecture for the Gross-Siebert model for local mirror symmetry. So I will particularly consider about the coherent sheaf, which is given by the direct image of the structure sheaf of some smooth curve inside the toric smooth toric surface, which is equivalent to some ample divisor. And in order to get to what the beta t should be, the basic idea is like this. So I will firstly compute the central charge of this coherent sheaf, and I will interpret the results with a combinatorial information of the polytope lambda c, which is just the polytope given by the ample divisor, which c is equivalent to. So in the P1 times and P1 case, for example, if we take C to be a degree 2-3 curve, then the polytope will just be given like this. So after this, I will identify. So in order to get the what beta t is, I will identify this polytope with a central component of the triangle minus the discriminant lobes, which is bounded by this discriminant lobes. And I will take a triangulation of this polytope and by taking U graph of it, which is just the blue part of that. So this blue part, through this identification, this blue part could be translated to some tropical one cycle inside our real affine manifold. And by Ruddat and Siebert's work, we can lift this beta tropical to some actual homology cycle inside the family YT. And I will show that the period of this beta t would be equal to the central charge of the coherent sheaf. Okay, so let me firstly compute the central charge of the coherent sheaf. Okay, so to do this, we need a couple of lemmas. So suppose C is a smooth curve, which is equivalent to some ample divisor. Okay, AI DI bar. So we have so this would be ample. So we have the following lemma. So lemma 1 is that the Chen character of the coherent sheaf inside the on the canonical bundle would be equal to D times D0 plus I have D0 minus D0 minus D times D. Yeah, so here D would just be the pre-image of the divisor of D bar inside the canonical bundle. Yeah, and we should have the lemma 2, which is that the intersection number of D0, D, and DJ to be equal to LFG. So LFG would be the affine length of the J facet of the polytope lambda C. For example, in this case, the affine length of F2 would just be 2, and the affine length of F1 would just be 3. Okay, and we have another lemma 3. The genius of CG would be equal to the number of the integer points of the polytope lambda C. So these are basically some results from the toric geometry, and I will omit the proof here. So with these lemmas, we can give the computation of the central charge. So recall that the central charge of the coherent sheaf will just be equal to sigma gamma k sigma bar 2 pi I degree over 2 Chen character of this one. Okay, so this term should be interpreted as the product of Tj to Dj. So this is actually given by the information of phi, the multivalued piecewise linear function. So recall that our phi is determined by setting vi to 0, 0, 0, minus 1, 0, 0, 0. So it should be expected that we have each Tj to Dj term for every j from 1 to k. And this term, the gamma term, will just be equal to exponential C1 kx sigma bar plus sigma nt minus 1 k zeta k k minus 1 hk t of x sigma bar. Okay, and this term, this term by the lemma should be 2 pi I square di times d0 plus I have 2 pi I cube d0 intersect minus d0 minus d times d. Okay, so in order to get the integral of that, we can see that this term is concentrated at degree 4. So we need to find out the degree 2 terms from these two terms. So since kx sigma bar is a non-compact Calabi-Yau manifold. So this term would be 0. So the only degree T terms were just from this term. And the result of the central charge will just be 2 pi I square sigma j from 1 to k log Tj LFJ. So Q pi Q 1 minus G. So this was just given by lemma 2 and lemma 3. So this is a affine length of jth facet of an MSC. And this is the genus of the curve C. Okay, so in this way, we can interpret the central charge by the combinatorial information of this polytope. So now, in order to get what beta T should be through the Gamma conjecture, I should give you the definition of what the tropical one cycle is. So the tropical one cycle would be embedding from a closed graph to the affine manifold paired with some section of lambda on each of gamma, such that the verticals of the gamma would all be trivalent, and the image of the verticals should be inside the interior of some maximal cell. And the image of the edge should only intersect the codimension one cell at isolated points. And it should satisfy the balancing condition, which means that at every vertex of graph, you should have the oriented sum of the section at that point should be equal to 0. Where epsilon EV is determined by the orientation of the edge at the vertex. So given any tropical one cycle, we can lift this tropical one cycle into an actual homology cycle inside the family YT. So in order to do this, what we actually need to do is we should decompose. Sorry, let me use a graph to illustrate that. What we actually want to do is that we want to decompose some beta tropical into a couple of subsets. So the blue one would just be the image, sorry, the image of H gamma. And we will decompose it into several types of different subsets. And we will do the lifting on each type of them. Okay, so let's call this to be type 1, and this type 2, and this type 3. Okay, so for type 1 subset, let's use the notation beta E. Okay, so what we actually need is we need to use the information of the moment polytope. So this is a moment polytope, a moment map, sorry. Moment map for the toric variety P sigma. Okay, so this will, you can regard, it will map complex torus to the interior of the maximal cell. So beta E would be some subset which is totally contained in a unique maximal cell and has no vertex. Okay, so you can regard this moment map on the interior of the maximal cell as some toric fibration, and it will have a special posterior real section, which maps the interior to the posterior real part of the pre-image. Okay, so in order to do the lifting, we can also regard this C star 3 as a home space from lambda sigma to C star with a natural torus action on it. S1 is equal to 3. Okay, so in order to do the lifting, we need to use the information of the section on the edge E. So recall that as this section would be you can regard it as an element inside the lambda sigma. So we will choose 2 subtories, which is given by theta, which is somehow normal to this CE inside. S1, T3. And then the lifting of that beta E, well, let's call it gamma I, will just be given by the action of these 2 torics on the positive real logs of beta E. Okay, so that's for type 2. So that's for type 1 lifting. So for type 2 lifting, so suppose the type 2 is some vertices which is connected to 3 edges. Let's call them E1, E2, E3. So at the pre-image of this vertex, we would have 3 orbits. So let's call this E1 V T E2 sigma V E3 sigma V. So this will be 3 2 cycles inside the pre-image of V, and it due to the balance condition. So these 3 2 cycles will bound 3 cycle inside the pre-image of the vertex, and we will just denote we will just use these 3 cycles to denote the lifting of the type 2 subset. So we can see that this gamma 2 could be defined up to some constant times of the fiber of this V. Okay, so for type 3, so for type 3, the tropical cycle will pass through some slab, and it will be contained in 2 different macro cells. So the lifting is basically, okay, so what we have is that we have an orbit here, let's say TE as sigma minus P minus, and another orbit at the point P plus, plus P plus. So this would be inside the spectrum, the affine chart of spectrum of lambda sigma plus. And this would be inside the spectrum of lambda minus. Okay, so the basic idea is that we want to represent this orbit inside some, we want to represent this subset. Okay, let me make it bigger. Represent in the spectrum of lambda sigma plus by using the local model of the spectrum of RV. And then we can glue this thing together in a canonical way. whose details I may omit here. So anyway, you could find a canonical way to group these two orbits inside the spectrum of the lambda sigma plus. And I will call this gluing to be gamma 3. Okay, so this is basic idea of how you can get from some tropical cycle to an actual homology cycle inside the family of YT. Okay, so next thing is that we want to do the period computation, which is just what this should be. So here's a holomorphic volume form. It's actually taken to be d log z1, d log z2, d log z3, with z1, z2, z3 to be the coordinates for any affine chart. So you can check that this holomorphic form would be well defined on the whole YT. And then this period would just be given by integrated 3 different types of lifting. And the result is that every type 2 lifting would give you a half 2 pi I cube plus up to some constant of 2 pi I cube. And every type 3 lifting will give you a term of 2 pi I square log of T kappa V. So kappa V is a kink. So kappa V is a kink at the slab which the type 3 subset goes through. And the rest of the contribution would sum to 0. So finally, what you get is that the period of the lifting beta t would be given by this formula. So P would just be the intersection of the tropical 1 cycle with the slab, and the signal of P will denote will be 1 if the tropical 1 cycle is the orientation of the tropical 1 cycle is from sigma minus to sigma plus. So V will denote the number of the vertices of the tropical 1 cycle, and C would be the constant, which depends on how many fibers you take at the second type lifting. Okay, so given this formula, we can try to compare this with central charge. Sorry, the central charge here. Through Gamma Conjecture. So let's firstly consider about a part of some tropical 1 cycle, which is given by this small loop. So I will denote the triangle minus the discriminant and log. So the triangle minus the discriminant logs will be decomposed into several components. Each component will corresponding to some vertex. So I will call these components to be G1, G0, G1, G2, G3, G4. So each component will correspond to some vertex of the of P. And I will call the edge of the central fiber to be F1, F2, F3, F4. So this will identify the central fiber with sorry. So this central fiber will be identified to the point of Lemmas C with facets identified through each other. Okay, so let me consider a special type of tropical 1 cycle, which is a small loop around some Fi. So according to the formula, the contribution of the period, the contribution of this tropical cycle to the periods will be from this to intersection of the small loops with slab. So this point will contribute to 2 pi I square log t to the q, and this point will contribute to 2 pi I square log t kappa v, which is equal to this one. So we can see a small loop which is around the edge fj will contribute 2 pi I squared log tj term into the period. So by comparing it with a central charge, we should expect that, so we see that the coefficient of the log tj terms inside the central charge is LFJ. So in order to match the log tj terms, we should expect that we have LFJ numbers of smooth loops around the edge fj. And also another thing is that inspired the SYC conjecture, inspired by the SYC conjecture, the support of the mirror of beta t could also be regarded as a lifting from the beta tropical, but just with T2 fiber to replaced by a dual T1 torus. So topologically speaking, the support of the mirror of the tropical one cycle, the support of the mirror of beta t should be expected to be a curve with genius equal to the number of the holes of beta tropical.
Excuse me, can I ask about the loops? I didn't understand. How is it a balanced thing?
I forgot.
Even if you assume like the monodrome, I don't see still how it closes into a balanced thing.
Yeah, that's a good question. Yeah, sorry, I forgot to say about that. Yeah, okay, yeah. So in order to let it satisfy the balancing condition, suppose we are taking the section to be 0, 0, 1 on this side, on the sigma plus. Due to the monodromy, after you go around this loop, after you parallel transport along the loop, this sigma 1 will be changed to this sigma 2, because it will pass through the slab. So since it will change, in order to make it satisfy the balance condition, we need to add another edge attached to the small loop with section denoted by minus VG bar 0, such that it will satisfy the balance condition at the attached point.
So I see. At this point, at this trivalent point, you also have the leg going inside your central region.
Yeah, exactly.
Okay, I think I understand. All right, thank you.
Yeah, thanks for put it with. Sorry, I forgot to mention that. Yeah. Oh yeah, so inspired by the SYC conjecture, we should expect that the number of holes inside the beta tropical should be equal to the genius of C. And in this case, it will just be the number of the interior points of lambda C. Okay, so given by this condition, the next thing is that how can we construct a tropical cycle satisfy these two conditions? So the idea is that you can take a complete triangulation of lambda C, which means that every triangle would be a primitive triangle whose integer points would just be its vertices. And then after taking this complete triangulation, you can take the dual graph of that, which just be the blue graph. And you can see that this graph will intersect every edge by a affine line times. So for example, here you have affine line 3, so the dual graph will intersect it 3 times. And also the holes of this dual graph would corresponding to the number of the interior points inside the lambda C. Okay, so in order to translate this dual graph to a tropical one cycle by identifying it with a central component, what we are gonna do is that you just take you just copy this dual graph to here. Okay. Okay, but in order to make it satisfy the balance condition, we should take sections on these edges, and you can take the section to be equal to the primitive vectors, which is orthogonal to its dual edge. Then, because every triangle is a primitive triangle, automatically, so the sections that you take would corresponding to the edges of it, the edges of the dual triangle of this vertex. So it will automatically satisfy the balance condition. And then in order to deal with intersection point with the edge, you can attach a loop to every intersection point so that it will satisfy the balance condition as shown in this diagram. And that's how you can translate this dual graph to a tropical one cycle inside the affine manifold. And then, according to the formula for the period, you can see that the period, you can see that their log TJ terms are matched. Okay, so that's for log TJ terms. So in order to match the constant terms, we actually need to add some more homology cycle into beta T by lifting a relative tropical cycle, which will touch the discriminant logs. And well, I may not tell too much about how to do this lifting, but just a way to do this lifting. And if you add this homology cycle together, you can regard their sum to be some lifting from some tropical curve. And according to Ruddat's work, you could figure out a Lagrangian representative of this homology cycle by regarding it as a tropical Lagrangian and smoothing it. So so then the constant terms of the period will contribute from the vertices and also from this relative, also from the lift of this relative tropical one cycle. And we will assume that each traveling vertex will contribute to a negative half times 2 pi I cubed to the period. And each lifting from the relative homology cycle like this will contribute a 2 pi I cubed. Then the constant terms from beta T and beta, the lift of the relative tropical one cycle would be equal to 2 pi I cubed minus a half the number of the vertices and 2 pi I cubed the number of the loops. So if you add them up, the number of the vertices is the number of the triangles of the triangulation plus the number of the small loops. So it could be translated into the area of the polytope minus a half the number of the lattice points of the boundary of delta C. And this will be the number of the lattice points of delta lambda C. And by Pick's theorem, this will be equal to 1 minus the number of interior points of lambda C, which would just be equal to 1 minus G. And this term will match with the result as in the central chart. So in conclusion, in this way, through Gamma Conjecture, I will predict that this beta tilde T would just be the mirror of the particular coherent sheaf that I consider about. Yeah, so I guess that would be the end of my talk. Thanks.
Thank you. Thank you very much. So,
any
questions? Please feel free to unmute yourselves and questions.
Can I ask? I have actually several questions.
Yeah.
One is like I think the interesting part in this gamma class is the gamma itself, the number, and the values of the data functions. And in your case, they're all gone, right? So you.
Yeah, right. That's a little disappointing. Yes. Yes.
So that leads to my next question. So what's so particular about this dimension 2? Because I see the point why you want the curve. I mean, your tropical cycle to be a curve. So you don't want to hit the discriminant. But what's so special about taking the surfaces rather than any other variety?
I hope I can generalize it to higher dimensional case. Actually, there's an example. So the reason that I haven't figured it out is that I cannot have a good description of the complete intersection. So if in 2 dimensions, a smooth curve could correspond to some ample divisor, right? So this ample divisor could give you the polytope, nameless C. So, for example, in higher dimensional case, I'm looking for some curve which might be equivalent to some complete intersection. So I have some difficulties to interpret this complete intersection as some tropical information. So it's basically that I cannot find a similar analog of this F lambda C for the complete intersection. But maybe there should be some answer.
But do you expect to see any of those values of the gamma function of the zeta function in this case, or is there still not going to be there?
No.
In your computation for this charge.
It will still not contribute to the central in this case. But it should be expected if you take a tropical surface and if it touches the discriminant logs, it will see the other terms inside the gamma class. So as long as it's only tropical curve, tropical curve will always can see the gamma class. But if you can think about higher dimensional tropical objects, and then there might be gamma class contribute to that.
That was actually my third question, because I know Diego Matesi, he worked some examples when he lifted 2-dimensional tropical things up to the, like in dimension 3, he could lift a 2-dimensional thing. Even if you hit the discriminant, but you hit it kind of, transversal way, it's not so bad. So he argued that you can still lift this thing into the total space as a Lagrangian.
Yeah. That's what I hope that I can generalize this result.
Because you're saying that this is the case when you can potentially see all the interesting terms in this gamma class.
Yes, exactly, and it's inspired. It's actually inspired by the result by AGIS.
Because they, as far as I remember, they actually see, see all the interesting terms there. But they, as far as I remember, they lift like the real locus, so they lift the whole three-dimensional base up, whatever the n-dimensional base up to the thing.
Yes, exactly. Yes. So in their case, they are considered about the Lagrangian sections. So the support of the, I mean, if you want a tropical description of that, then the tropical object would be the whole space. would just be the whole space, I think. Oh, yeah. Yeah, so in their case, they are considered the battery mirrors. So the Lagrangian section would be the tropic object would just be the whole space of the polytope, and it will contain all the discriminant logs, and they have some local analysis around these discriminant logs, which will contribute to.
Because that seems to be like the very interesting, I mean, the discriminant seems to be giving you, more kind of very, very interesting information about all this.
Yes, that's.
Can I comment?
Yeah, sure.
Sorry, I had trouble finding the link, so I came a little late. So what I say might have already been said at the start of the talk. But yeah, certainly the work of Abouzaid, Ganatra, Iritani, Sheridan, in finding, this these zeta functions was inspirational, as Junxiao just said. And then on the other end, it's the work of Ruddat and Siebert, and maybe the longer term project here that Junxiao is describing is to sort of get the best of both worlds, which would be the surface case. So it's something that's not a section, a line, and something that's not codimension 2, a curve, but something in between. But already in trying to get there, this turned out to be an interesting problem in its own right.
But as I said, so like I remember Diego Matesi has done some work in dimension 3 case for lifting 2 dimensions.
Yeah.
All right. Thanks.
What is the exact reference for Matesi's? Is that?
I think I don't know if he actually published anything, but I've just heard several talks of him. Just type Matesi and search for his papers.
Thanks for the information.
I know they're finishing something with the Ruddat, probably something close to what something about this the Lagrangian stuff. Probably very soon there are going to be some new stuff appearing.
Okay, thanks. Yeah.
Thanks, for it was a very, very inspirational talk. Thanks.
Thank you.
Any other questions? If not, thank you a lot for a very nice talk, and I guess that's it for today.